So, this one shouldn't, I should kill the lights. This one shouldn't take us too much time to get through. This is kind of working towards some of the accreditation requirements for this class. I have to make sure that you guys know a little bit of digital design. So let's talk about digital circuitry. I imagine you guys probably did a fair amount of this last semester, so this should be mostly review. Don't everybody get up at once. Jokes, am I right? So, transistors. The fundamental building block of all digital electronics is the transistor. This is what's called a MOSFET, or a metal oxide silicon field effect transistor. It differs from the other sorts of transistors that you will see because rather than having the P and N-type silicon directly abutting each other, you sort of have this sort of two N-type crystals swimming in this pool of P-type silicon, which then has an electric field imposed on it by the gate voltage, right? So, how many people remember how a transistor works? I got maybe half a hand. Okay. So, anybody know what P or N-type silicon means? Okay, we're going to have fun today. A little bit. All right. We'll get into semiconductor physics. Just a little bit. And not many, like this is the only slide on it, but it's important to understand what a transistor is if you're going to use them for a bloody living. So, silicon. Silicon as an element on the periodic table of elements. Where does it reside? What group's it in? Metalloids. Thank you. Why is it a metalloid? It has the properties of both a metal and a non-metal. In the particular case of silicon, it is conductive under certain circumstances, and non-conductive under other circumstances. This is what makes silicon ideal for the switching applications with which we use them for. So, does anybody know how these types of applications were performed prior to the invention of solid-state electronics? Not in your head, no. So that's a good guess. Yeah? Mechanically, yes, using relays. So, what a relay is, right? And if you go into an industrial plant, open up one of the control panels, you'll still see many, many relays because relays are, they're still used in like high voltage, high amperage situations, right? But essentially, all you have is a solenoid coil, right, with a metal arm here and a magnet or a ferromagnetic material here. So if you energize the solenoid coil, produces magnetic flux, pulls this guy down, makes contact with some other contact, closes a switch, right? Basic electromechanical switch. These are still very much in use today. Vacuum tubes less so. Vacuum tubes have a, I should have watched a video on how vacuum tubes work if I was going to talk about this today. Vacuum tubes are mysterious. They work on the mysterious universe juice of the universe. I don't know how they work. Anybody know how a vacuum tube works? Anybody? Well, it doesn't really matter. Yeah, Beauty?
Like a cathode ray tube?
No, cathode ray tube is different. So, prior to the invention of cathode ray tubes, you had these little bulbs, right? They would kind of look like this, right? And you would screw them in, and they'd have certain filaments inside of them, and it had like similar effect to the relay, but it had to be encased in like a non-oxidizing gas, right? It had to be purged of oxygen, otherwise it would catch fire. Kind of similar to the incandescent light bulb, right? So anyway, this is what like the electronics of the you know, 30s and 40s and 50s looked like. You know, it's a derivation of the incandescent light bulb, right? Yeah, so like old ham radios, for example, use vacuum tubes. They're very large, but, you know, essentially also act as electric switches, and they were, you know, they consume slightly less power than does the relay, but, you know, not at all miniaturizable. The computers of the 1950s and 60s, prior to the miniaturization and the development of the microcomputer, the reason that a computer would fill a room like this is because every transistor in it was one of these guys. And they would occasionally burn out, so you needed a technician who knew where all the transistors, or who knew where all the vacuum tubes were, and could like pull them out and put them back in and like get rid of the bugs in the circuit. Like, you guys, did I talk to you guys about like the origin of the term bug, like computer bug? In two P? Oh, good. Okay, I'll leave it there then. But yeah, so in the 1950s, although like the scientific development was ongoing for quite some time, but primarily sort of late 50s, early 60s, we had a quantum leap forward in the development of such technologies known as solid-state electronics. The metalloid properties of silicon are employed to produce a device which can either block or permit electron flow based on the voltage state of a third pin. This is actually like the way that diodes work as well. So, silicon, right? Silicon forms a crystal matrix. During the process of crystallizing the silicon, you can put certain additives into the silicon which cause the silicon to hold either a positive or a negative permanent electric charge, right? This process is known as doping. I believe, I could be wrong about this, I believe positively charged silicon is doped with boron and negatively charged silicon is doped with arsenic or something along those lines. I could be wrong about that. Anybody, if you have a computer open, please feel free to fact check me on that. But at any rate, two different elements in the periodic table, if used during an additive during the crystallization of silicon, produce either positively or negatively charged crystal, right? Now, the advantage of something like this is that, unlike the vacuum tube, this guy ended up being super hyper miniaturizable. Like what are these again? Transistors. The transistors that are produced in like all of the laptops and cell phones and all of those things that you have sitting on your lap. The transistors inside of these processors are measured in number of atoms across. That's how miniaturizable this technology was. And that is the only thing that has, like, this is the scientific development that has, produced the modern age with respect to communications technology and information technology. Everything is based on semiconductor technology. If we hadn't discovered this, we would still be using vacuum tubes, or maybe slightly better vacuum tubes. But, so how does it actually frickin' work, right? So, very roughly speaking, we'll start with a diode, right? So what a diode actually is it's a region of N-type silicon directly opposing a region of P-type silicon. N is negative, P is positive, obviously. So if this is n-type, and this is p-type, right? What n-type actually means is that there are extra electrons in this, right? So you'll just have some free-floating electrons, right, that are just kind of in here. In the case of p-type, what you have is, well, they call them holes, but it's like gaps in the orbital structures of the atoms where the electrons should be, right? So I know I did these as circles, so I know it doesn't make any sense, but I'm going to do them as squares. So holes are squares, right? So one question that might arise, right? Why do these electrons not just immediately jump over and fill these holes? Right? The answer is that they're bound more tightly by the atomic forces of the atoms than they are attracted by the opposite charge. So they stay where they are. Right? So essentially, a diode is a device which allows current to flow in only one direction, right? So, oh my god, I can't remember whether it's this way or that way. Ha! I'm going to have to look it up. Give me a second. I forgot. I should have written it down. No, not my email. Get out of there. Diode. How does it work? Let's see here. Come on. Jeez. Anyway, while I'm getting that to load, yes. Images, quick. Okay, so it flows from the p-type to the n-type. Good. So, there we go. So, flows from p-type to n-type. So, flow is allowed in one direction and not allowed in the other. This is the symbol for a diode, right? The symbol for a light-emitting diode is this thing with little beams of light coming off of it, maybe in the other direction, like so, at any rate. So, what happens when you have a bunch of electrons crowding up on this side, right? They jump into the holes and then keep flowing, right? If you have electrons on this side, they'll be repelled by the negative charge on these electrons here, right? So there you go. Diodes, okay. So the field effect transistor, right? What you have is you have a field of the p-type silicon with regions of n-type. You have a plate here which is connected to a wire, and you have two wires which are connected to these two terminals. Right? So, when this guy in the middle does not have any charge, no free electrons floating around in it, we're just in the situation we see before us. Whether this side or that side has the positive voltage, it can't cross the p-type gap, right? So, when you charge up this plate, you get you induce an electric field, right? You induce an electric field into the p-type silicon. This allows a little channel near the surface to be of a sufficiently correct charge for the free flow of electrons to occur, and that opens the gate, right? So when you apply voltage, a little gate opens, otherwise it's closed. And that's how a transistor works. Does that make sense? Good. So, so essentially, it's really just an electric switch, right? Oh, there we go. Good. So, the question then becomes, how do we use that, right? How is a switch useful to us? Well, I mean, actually, I shouldn't even have, I pose a question to myself which is so obvious I won't even answer it. It's useful to be able to direct electrons where you want them. So, binary logic circuits perform operations where signal values are restricted to 1 or 0. If we take a circuit and we put multiple switches in that circuit, right? In this particular case, in order for this light to go on, both switches must be closed. This corresponds to a Boolean AND operation, right? Because both x1 and x2 must be closed in order for the current to flow. So in series is AND. In parallel is OR, because if either x1 or x2 is closed, then the current can get to the light, or the load. Make sense? Good. So far, so good, right? So let me just see that I didn't miss anything important here. Okay. So, we're going to talk about circuits. We're going to use a sort of a formulaic formulation. That is to say, circuits can be described as functions, right? However, you have to impose a very specific and particular set of operations on them in order to make it work. Basically, you have to slightly modify the definition of addition in order to make it work. So, if we have, x1, x2, x3, right? And let's say we AND these guys together, and then we take the OR of that, and that becomes L at x, or the output of the logical function, right? When we are ANDing things together, this is essentially the same idea as multiplication if you examine it from the perspective of ones and zeros, right? So anything multiplied by 0 is 0. So if you have two values which are constrained to only be 1 or 0, they will only be 1 if either of them are 1, right? So AND gates are multiplication, right? OR gates, on the other hand, addition with one caveat. If we define 1 plus 1 as equaling 1, then everything works, right? Because there's no concept of 2 here, right? It's either on or off. So, a logical expression for this particular circuit, we would say L at x is equal to x1 times x2 plus x3. Make sense? Is this like visible for you people over in the corner? Okay. So this is fine, but there's one more piece of the puzzle that we need to be able to understand these circuits. If we invert one of these symbols, we put a bar over top of it. So for example, if it was x1 plus, or x1 and the inverse of x2, this is an inverter, right? Then we put a little bar over it. You'll sometimes see this circle moved around. Like this could be expressed in one of several ways. It could be expressed with an inverter separately itself. It could be expressed with a little circle on the input lead that also negates the signal. And you can also, like you will often see a little circle on the output port of a logic gate that negates the entire symbol, so that would be like, you know, something like that, right? So that's, with these components, we have pretty much everything we need to express these guys as logical formulas. Have I said anything yet that isn't review? Not really? Okay. Is this good review at least? Okay, good. So, good. Yep. So, and, or, and not are the basic building blocks of logical systems and can implement all logic circuits. Technically speaking, all you need is and not. So there's this interesting property of logic where you can identify a minimal set of operators from which all other operators can be derived. This is occasionally useful when you're trying to like prove things in like formal mathematical logical space that you guys probably won't have to worry about. But for the purposes of real design, it's useful to have all of the different gates. So I just thought that was an interesting point. Anyway, so I imagine you guys have seen truth tables before. I should certainly hope so. So, just as review, here are a bunch of different logic symbols. Where's my... There we go. So this is a driver. Note the absence of the little circle symbol on it. Kind of looks like an operational amplifier, doesn't it? AND gate, OR gate, XOR gate, inverter, NAND, NOR, and XNOR. Or SNOR? Is it a SNOR gate? Maybe, I don't know. Anyway, so you can see each one of these has an inverted version by putting a little circle on the end. The XOR gate notes that it has a different symbol, right? So when you're expressing XOR in the form of one of these equations, like for example, if this were an XOR, you put a little circle around it. Right? Good. Oh, and you'll sometimes see inversion represented as a comma instead of a bar over top. Just in case. So, a complex logic system is implemented by several logic gates interconnected together called a logic circuit or a network. I sometimes use the term combinational logic to refer to this. You have combinational logic, which is composed primarily, exclusively of logic gates, and then you have sequential logic, which requires sequential components that we're going to be talking about, like flip-flops, right? You guys all remember flip-flops, right? Not for going to the beach with? But yeah, so a designer must be able to figure out the function performed by a logic open network. Analysis, yes, obviously. A more important task is to be able to design a circuit that implements the desired behavior. So, let's talk about this circuit here, right? If we were to derive a truth table for it, just kind of by analysis of the circuit, and F, there we go. Right? What's the case if both of these are true? What do we get? True, thank you. What if x2 is 0? Zero. What if x1 is 0 and x2 is 1? Right? And in the other case, when both are 0? There we go. Truth table derived. So, one thing that we might note about this, my shoelace is undone. That's not about that, that's about my shoe. Let me just fix the shoe then. There we go. All right. So, we're using 3 gates here to represent this equation, or this circuit, right? Do you think we could do better than that? Yes. Yes. How could we do better than that? Can you find a representation of this outcome which uses fewer logic gates?
Maybe NAND? I don't know.
NAND isn't the answer to everything, man. Come on.
I mean, it could be. I didn't want
No. So, if we think about this in terms of the truth tables that we know and love, right? If we have 3 on and 1 off, which of our basic logic gates also has 3 on and 1 off? OR gate. So, if we're allowed to invert these symbols, how could we derive an OR gate from this?
Invert x1 and then run them through the OR gate.
Yes, invert x1. So if we invert x1, 0, 0, this becomes 0. That's a 1, so there, and there, and there. So, in fact, we can express that whole entire thing much more simply. Right? Even if you expand this circle out to a whole darn inverter like it is right there, that's 1 less component. Right? So, one of the things about logic is that you can have many, many different logical circuits which all have the same outcome from the variables, right? Like, they don't have to be like obviously useless to be equivalent, right? Like, you know, obviously if I want to take the AND of two symbols, right, or two signals, I could just do it like that, or I could do it like this, right? Same functionality, but it uses 3 times the silicon, right? No point in that. Just keep it simple, stupid, right? So it turns out that minimizing the number of logic gates that you actually require to perform a task, that's actually a design thing. You can design that, right? The less silicon your product requires, the less money it's going to cost. Obviously, a logic gate isn't expensive, but it's, you know, it's the principle of the thing. So, good. So we construct the truth table. Consider, yes, 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 there we go. That's there. That's the slides' version. Like, what is even going on with these wires, man? You know? But anyway. I will try not to be too critical of the fact that, like, right here you actually have a break in the circuit, which means the whole thing wouldn't work anyway, but, you know. I'll try not to be too critical of slides I didn't make. But anyway, so we can have equivalency between logical circuits. We can actually use principles of algebraic simplification on formulas in order to minimize logic, right? This is like kind of what we did. The approach that we just used is kind of like an intuitive approach to the problem. So let's attempt to do it slightly more systematically than that. So I'm going to start off with Karnaugh maps. Because I think Karnaugh maps are actually the best one. But anyway, so let's imagine, so another way of representing truth tables is thus. It's a slightly more compact notation. Let's say we had A, B, C, D, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1. And let's just, okay, call out random binary digits. 10 isn't a binary digit, come on. All right, fine, 10. Next.
0.
Thank you.
1. 0.
Eh?
1. There is 1. Oh, all right.
Yeah.
1, 0, 0, 1, 1, 0, 0, 0. Oh, God.
Yeah. Sorry, I need those to be there. So, the purpose of a Karnaugh map is to avoid having to do algebra. So, yay. So, what you're doing is you're looking for groups. I'm going to add one more right here. There. There we go. So, you're looking for groups, right? So, you're looking for clusters of 2 or more, but they have to be like adjacent. So this is a cluster right here, right? This guy right here is a cluster as well. This guy is just on his own. And I guess that doesn't work, does it? Oh well. These guys are also lonely.
No, those aren't those two clusters with each other.
I mean, but you've got...
But they like, they connect on the other side.
Yeah, I just... Like this?
Yeah.
Yeah.
You have to use gray code.
You have to use gray
You
code.
have to swap the 0 line to 1 line.
You have to...
Change one bit at a time. Yeah.
So 0, 0, 1, 0, 1, 1, 1, 0, 1. So.
You guys want to teach the class? All right. Anyway, so the fundamental technique, right? You take an area like this. You identify which of these signals are constant for that area, right? Like for this area right here, B, like not B, not C, and not D, right? Because B is 0, C is 0, and D is 0 inside of that area, right? So that is one term of the eventual equation, right? Because it doesn't matter what A is doing, right? Like technically speaking, if you say A, B naught, C naught, D naught, plus A naught, B naught, C naught, D naught, you can say B, C, D, A and not, or A or not A, which is just nonsense. So then you're left with this anyway, right? So anyway, so you do that. The larger the section is, the more numbers, the fewer numbers you have in the eventual term, right? So in this case, the things that are constant are B and oh shoot. What was it again? You take the.
Oh, you need to switch the 1, 0 into the 0, 1.
You switch.
No, you switch 1, 1.
Right, yeah.
1 and 0, 1 swap. 0, 0, 1 change.
No, it should be 0, 0, 0, 1, 1, 1, 1, 0.
The first column should be 0, 0, the second column should be 0, 1, the third column should be 1, 1, and the fourth column should be 1, 0.
Yes.
Doesn't matter.
Yes.
Okay. Oh, right. They need to be adjacent. Yeah, okay. I know what's going on. Thank you. All right.
The A, B, the second one is also.
There we go.
No.
What?
Oh yeah, no, that works as well.
Yeah. There and then. All right. Thank you for that class. I appreciate it because, you know, I know I look young because I have a bad haircut, but I'm very old, and it's nice to know that other people have looked at this as well. But anyway, yes. Anyway, so yeah, sorry, pardon me. So and I know that messes up all of the bit values, but I'm going to do it anyway. All right. So we can make the observation that both these guys and these guys are held constant at that time. So in that case, we're looking at B and C. Yeah, so there we go. And you can just go through the whole thing in similar manner. Join all of the terms with OR operations, and then that gives you your equation. You can then take the equation, implement it in digital logic, right? The idea with a Karnaugh map is that if you have correctly used the minimal number of groups that's possible, then you come up with an equation that's already minimized, right? But anyway, when you have a digital logic expression which is expressed as either the sum of products or the product of sums, these are known as canonical forms, right? So the object is to get things into canonical form because, you know, it's easier to work with, essentially. So, good. Where are we going? All right. So, anyway. So, the sort of alternative method to this is to derive everything out using algebra to its full extent, and then use the table to derive everything out to its full extent using all the terms, and then simplify it algebraically using the types of simplifications that I demonstrated over there. So if we took, for example, the following truth table, right, which is the same truth table, we can see that not x1 and not x2 yield 1, not x1 and x2 yield 1, and x1 and x2 yield 1. The final one does not. So, basically you go through each row in the truth table. You write out the terms that correspond to the answer being true, and then you take the sum of all of those. That gives you product of sum, right? So, yeah, does that make sense? Crickets. Okay. Is everybody kind of just done with this class? No? Yeah? Okay. I don't know. Anyway, so in the previous example, the equation that we come out with is precisely those terms listed, joined with OR. So you can tell, however, this is not, while this is in canonical form, this is not a minimized form, right? Because if we were to express this, all the way out, we'd get some long, complicated Cthulhu, like, x1, x2. Do we have any not x2 in there? Yeah, we do. So we got these guys. We invert them as well. Come here along. We have a big OR of 3 ands. Not. This one, and regular, and both true. Obviously more complicated, right? So, yeah, exactly. So, if we wished, however, to perform algebraic simplification of it, which I will attempt, we'll see how I do, Given how things have gone today so far, who knows if I'll be able to pull it off, but I'll try, goddammit. So we have x1, not x1, not x2, or not x1, x2, or x1, x2, right? So we can collect these guys, right? So we got x2 or not x2 is always going to be true. So we can cancel that term. Right? So we result not x1 plus x1, x2. I don't know. Anybody got an idea where to go for here? Yeah?
I don't have like the proof for it, but the x1 is redundant.
The x1, this guy?
Yeah, because if you're not x1, you're already x1.
True. Alright, good enough for me. Anyway, so, it's logic, so logic should be an applicable method, right? So, good. So, we're going to discuss a couple of, all right. You guys remember when I was talking about multiplexers way back at the beginning? Well, oh my God, no, shush, get out of here. No, that's worse, stop. Destroy you, thank you. So, just to review, a multiplexer is a circuit which selects between other circuits. Basically, if we have two inputs, x1 and x2, if the selector is 0, it picks x1. If the selector is 1, it picks x2. If you expand that out to a full truth table, it looks like that. But if you were to implement the multiplexer on one bit, this is what it looks like, right? You have x1 and x2 coming in, both to AND gates. The selector bit will turn on, essentially, the one AND gate if it gets a 0, and the other if it gets a 1. In either case, we combine the two signals to get F. Only one of these two signals will be, like, only x1 or x2 will be allowed through at any given time. If you take this and you multiply it by the number of bits that you have in a register, and then you multiply it again by the number of different data buses that you want to multiplex, then these types of things are very commonly used, right? Like, the thing that selects which register's data ends up in the ALU in the processor is one of these guys, right? Anyway, all right, get lost. Take her easy, folks.